Hello, so continuing on weekly contest 344, the last problem, make costs of paths equal in a binary tree. So this problem says basically that we have an integer n that represents the number of nodes in a perfect binary tree. So by perfect here, it means that all the leaves are filled. And then we have the nodes are numbered from 1 to n. We don't get the binary tree itself, but we do get the structure where basically the node has an index. So for example, I, and then the children would be 2 multiplied by I, and then 2 multiplied by I plus 1. Okay, and each node has a cost that we get here as an input. And so this array costs of size n, where basically cost I is the cost of the node at I plus 1. So just some small challenge here where it's 0 indexed and then the nodes are numbered from 1, so we just have to be careful there. And then in the problem we are allowed to increment the cost of any node by 1 any number of times, so we can increment by 1, but you can do it multiple times. And the goal of the problem is to return the minimum number of increments that we need to make so that the cost of paths from the root to the leaf nodes are equal for all paths. Okay, so that's what we are asked to do here. And then here it just explains that a perfect binary tree is a tree where each node except the leaf nodes has exactly 2 children, right? And so the cost of a path is just the sum of the cost of nodes in the path. So for example, for this path, the cost is 1 plus 5 plus 2. So that's the idea. Now let's take a look at an example here. So we get n equal to 7. So that means we have nodes from 1 to 7. And this is the cost. Okay. And so what are we asked to do here is return the number of increments to make all the paths. So this one, this path, and then this path. You get the idea. All the paths equal. So how do we do this? So for example, in this case, what we need to do is first we need to increase the cost of this node, right? 1 time, so we need to make it 3. Okay, so once we make this 3, then at least this path here and this path here are equal, right? Because they would be 1 plus 5 plus 3 each. Okay, so we need to increment 1 time already, so that's the one here. And then for this one, we need to increment this 6 here. For this node 6, for node 3 here, we need to increment it by 3. So it becomes 5 if we increment it by 3. And then this node here, we need to increment it by 2 so that it becomes 3. So you can see we are sort of making them equal. And so that way, this path, 1 plus 5 plus 3, is also equal to these 2. And then it's also equal to this one. Okay, so that you get the idea, and now if we add these together, we get 6, and so we return 6. So that's the idea. Now let's see how we can solve it. Okay, so how do we tackle this? So just looking at what we had to do for this path in the example, we had to update this to match this, right? Because if we don't, they both share the same parents, right? They share this one, which has the cost of 1. They share this one, which has the cost of 5. And so if we, this one here is 2. So if we don't make these 2 equal, then this path and this path will never be equal. Okay? And so right there, that means we would have to change this one to 3. So we would have to do plus 1. Okay? Now, what did we do here, actually? Well, we just updated. So if we generalize this, let's say this value was A and this value was B, what did we do? Well, we just made B equal to A. So if we generalize it even more regardless of the value, we just make both equal to the max of AB. Okay, and what are the AB here? Maybe a better notation is just left and right. So we just made both equal to the max of left and right. And so this is just like on a tree of just one node and one child, or in 2 children, right? And so we can generalize this actually to the entire tree. And so how do we do that? Well, so you can see here, what is the cost? What is the increment that we added? Well, we know that we need to make both the max of both. So what is the increment that we need to increase? Well, we just take we have two children, so we take the minimum, we make it equal to the maximum of the two. And so what is the increment? Well, the increment is just the difference between the max of the two and the min of the two. Because we will need to add this difference to this one to make it equal to this one, right? And so that's what we need to do. Now, what are we using here? What should we use? Well, we should use, of course, DFS because we will need, once we make these equal, we will need to also make these two equal because we also want this path and this path to be equal, okay? And so that's where here, what needs to happen is that each node needs to give its own cost to the parent. So what will happen is that this one will say, now once we update it, it will say, okay, 3 for me, 3 for me. And so this one, what's the cost of this one? Well, it's not the sum of both, it's just one path, because now we made the two paths equal. We just need to know the cost of this path, okay? And so it's just going to take 3, so it's just going to take the max of the two. This is the return of the DFS. It's going to take the max of the two plus its own cost, right? Which is, because this is indexed, if this was I, because this is indexed from, because this is indexed from 0, we'll just need to do I minus 1, right? So this is just going to be a cost I minus 1 because of the indexing. But once we do it, this will return, this will be 3 plus 5, right? That's just the path from here going all the way down for both children, right? And so this would be now, this would return to its parent the sum. And so it will return 5 plus 3, which is 8. Okay, and then we do the same thing here. Now, this one is 3, this one is 1, so the max is 3, so we need to update this one to be the max, so 3, which means we need to do 2, which is 2 increments, right? And so now this will say 3, 3, and now this will do the same thing, and now this would be, instead of, it will return to its parent 3 plus 2, so it will return 5. And now we do the same thing recursively on these two. So this child says 5, this child says 8, so we need to make both of them equal to so we need to make the other one equal to the max. And so that means we'll need to change this one to update it to be 8, which means we will need to do an increment of 3, okay? And now at this point, what will be returned at the parent, it would be just 8 plus 1, which is 9, but we don't need to continue because that's the parent node, the root node, right? And so if we take all the increments we did so far together, what's the cost? So we did plus 2 here, we had to do plus 1 here, and we had to do plus 3 here. Okay, so that's 1 plus 2 plus 3. Overall, it's 6, and that's the final result that we return. Okay, and so again, for these problems, usually try to solve it on like the smallest tree possible. So here we started solving it with just one node with 2 children, and then we generalized that to the overall tree. And then also here the main insight is that we need to make each path equal. So and we need to just return to the parent the sum of one of the paths because we already made the other path equal to it. Okay, and that's pretty much it. So the time complexity would be just the of E plus V because it's DFS, and so the number of edges and the number of nodes, that would be the roughly O(n). Okay, now let's implement this and make sure it passes. Okay, so let's implement the solution we just saw in the overview. So we need to do DFS, right? And so our DFS, we need to start from a node, and we start from the first node, which is 1, because the nodes are from 1 to n. Okay. And then we need our total increment that we'll need to return. And then this is what we'll need to return at the end. And now we'll just do our DFS, right? And so we need a left side, we said, and then we need a right side, okay? So for the left side, we know it's just 2 multiplied by I. The problem tells us that. And then the right side is 2 multiplied by I plus 1. And then we said that each one will return to the parent the max of both, plus its own cost, right? So its own cost is I minus 1 because of the indexing. And then with the max, because we'll make the minimum of the left and right equal to this one. So both will be equal, have this cost. And so to do that, we will need for the increments to make both equal. And so to make both equal, one of them is already equal because it's the max, but to make the minimum equal, we'll just subtract the difference that we'll need to add, right? And that's pretty much it. Now we just need to add our base cases. When are we done? Well, we are done when we reach the leaf, when there are no more children, right? And so how do we know there are no more children? We know that we have up to n, the nodes are up to n. So if the left child, which is the smaller one, is bigger than n, that means this is a leaf node, and this is a child of a leaf node, so it doesn't exist, so we should stop and return 0. Okay, so that's the idea here. And so this should work. Let's run it. Looks like there is a small error here. Let's see where. So we take the max of the left and right, we add the cost, and then we get the min. Okay, and then, sorry, this is not n, this is the length of cost. Okay. Okay, actually we can keep n, but just this is I. The node itself is bigger, because if we do 2 multiplied by I, this means we are actually in a leaf node and we won't process the leaf node, and that's bad. So we just need to check the node itself is beyond the node that we should take care of. Sorry about that mistake. And now this should pass. And that gets accepted. Okay. Yeah, so that's pretty much it for this problem and for all problems of weekly contest 344. Thanks for watching, and see you on the next contest. Bye.